Alrighty, good afternoon, everybody. Here we're going to be going over the first bunch questions from Unit 1. And so we'll go ahead and get started here with the first question. It reads, spacecrafts A and B are flying parallel to each other through space and are next to each other at a time t equals 0 for the interval such that t is greater than 0 seconds but less than 6 seconds. Spacecraft A's velocity VA and spacecraft B's velocity VB as functions of time are given by the following equations. T squared minus 5t plus 20 for A, and B's velocity is t squared plus 3t plus 10, respectively, where both velocities are in units of meters per second. At t equals 6 seconds, the spacecrafts both turn off their engines and travel at a constant speed. First question. At t equals 0, is the speed of spacecraft A greater than, less than, or equal to that of the speed of spacecraft B? So let's go ahead and see here. So at t equals 0, we just need to evaluate this function. Both these functions at 0, and so the velocity, and I think that's a little thick, we'll go ahead and reduce it in thickness. Let's be a little drastic and see if we need to go halfway. So the velocity of A at 0 seconds is going to be, well, t squared is 0, 5t is 0, so that's just 20 meters per second. And the velocity of B is going to be, we do the same thing, 0 squared is 0 plus 3 times 0, 0, 0, then that gives us a total of 10. So it appears to me that the velocity of A is greater than that of B at this time. And what would be our justification? So because we have to be very careful to answer this part, right? Not only are we being asked to evaluate or compare, but we also need to justify. So we could say essentially this, but in word form. T equals 0, the value of VA equals 20 meters per second, and VB is 10 meters per second. I think we can go ahead and say that. Okay. We can look at the scoring guide and see what they were looking for. So let's see here. So we can go into our OneNote, jump to the scoring guide for this part, and let us see here. So this question, or this portion here, was worth 2 points. 1 point is for selecting greater than and for a justification. So let's go ahead and see an example of their response. Justification. If you substitute t equals 0 into both equations, the velocity of A equals 20 and the velocity of B equals 10. Thus, at time t equals 0, the speed of spacecraft A is greater than that of B. Okay. So pretty straightforward. Let's go ahead and look at the next portion of the question. Each spacecraft fires its thrusters for speeding up and reverse thrusters for slowing down. At time t equals 0, one of the spacecrafts is slowing down and the other is speeding up. Which spacecraft is slowing down and which one is speeding up? So again, we need to do some functional analysis here. So if we look at this, the initial velocity of both these spacecrafts are positive. So the initial velocity of A was positive 20 meters per second. And the velocity of B at 0 seconds is going to be 10 meters per second, also in the positive direction. Now, to be speeding up and slowing down, we need to make a comparison between the direction of the velocities and the acceleration. And so if we recall, if the sign or direction, really, not sin, but like sign of the velocity equals the sign of the acceleration. I'm doing it again, I apologize. I'm talking about the sign, positive or negative, really the direction. But when we have a function here and we represent these functions with directions, negative means in the opposite direction. So the sign there is helps us out. So when the velocity and the acceleration have the same sign or the same direction, we are speeding up. Remember, these are vector quantities. We cannot just say deceleration is automatically negative. Because, for instance, if I have an object moving in the negative direction with a positive acceleration, that object is decelerating. But the sign of the acceleration in that second example would be positive. And then if the sign of V is opposite, All of a sudden I feel like I'm misspelling it. You write a word so much and then it starts to look funky. So the sign of the velocity is opposite. Or, my goodness, I need to slow down. Opposite the sign of the acceleration, then that tells us that we are slowing down. So let's see here. Well, where are we going to find the acceleration in these two equations? Well, we have to compare this to the displacement or even position equation. Sorry, I am, for a moment there, I saw the quadratic and I was thinking position. That is incorrect. This is a function of the velocity. So this right here is not the acceleration. This is actually something called jerk, or the rate of change of acceleration. So we're not going to be worrying about that. If we compare the velocity equation for constant accelerations, if I take the initial velocity plus the acceleration times time, that's going to give us some velocity later. So if we look at this, when we have a velocity function, the linear term is actually what represents the acceleration. So here we can go ahead and determine, okay, well, what is the acceleration sign comparatively? So we have -5 for the acceleration, and then another guy, and the initial velocity is positive. So these guys are going to slow down. Okay. Interesting use of highlighters. If we look at the velocity and the acceleration for spacecraft 2, in this case, they have the same sign. They're pointing in the same direction, more importantly. I keep saying sign, but again, this is just because we're representing it with an equation. The important thing is the direction. So because these two vector quantities have the same sign, they are in the same direction. So we're going to get faster for B and slow down for A. So which craft is slowing down? A. Justify our answer. The acceleration for spacecraft A is in the opposite direction of its velocity. So the velocity is going to change in the opposite direction, therefore diminishing the value or the magnitude of that velocity. So let's go ahead and see here what the scoring guide was looking for. So for part B, spacecraft A is slowing down. If you take the derivative of both and substitute in, oh, okay, initially, that's actually a better way to do it, especially we're talking about a calculus-based physics class here. So we should be probably thinking if we can justify with derivatives and calculus talk. But I think implicitly we did say that the acceleration is negative for B, for A, and for B it's positive. Since both have had a positive velocity, the spacecraft A must be slowing down. Okay. So there we go for that. If we're wondering how do we take the derivative of this, right? We have a polynomial, so the acceleration of A as a function of time. So we do our polynomial rule here. And so that becomes 2t. Welcome, welcome. I went ahead and started recording this session just so for the sake of just building some momentum here. So this right here represents the acceleration of spacecraft A. As a function of time, we plug in a 0 for the time. And so now we know the initial acceleration is going to be, well, 0 times 2, 0 plus 5, 5 meters per second squared. And I'm sorry, I made a mistake here because I lost the negative. It tends to happen when you move a little quickly. That's going to be negative in contrast to the initial velocity here, which was positive. And then we do the same thing for B. And so the acceleration of B as a function of time is going to become 2t plus 3 with an initial acceleration of 3 in the positive direction meters per second squared. Okay, so let's go ahead and look at part C. We're actually going to have to do some calculations. Now, if we look on our AP Classroom, I went ahead and I shared with you the action verbs for free response questions. And so when we have to calculate, we're going to have to plug in some numbers and show some of these quantities here. So calculate the time interval which the spacecraft selected in part B is slowing down. Calculate the value of t at which the two spacecraft are traveling at the same speed. So this is going to be a secondary part. Sorry, I just realized that this right here, part 2, is in reference to part B. So this is the second question in reference to that. So we're going to hold off on part C. So here we have to calculate the time t. Sorry, again, I am misreading. Sorry for not formatting the PDF better. That way we could get a little bit more legibility. It's the selected spacecraft is slowing down. Okay. Alrighty. So there are a couple of ways to do this. Where is my draw? Okay, sorry, I was just trying to bring back. For instance, we're talking about spacecraft A. I'm going to work off to the side here just because I don't have enough space to maintain legibility. But I'm going to go ahead and copy down the velocity equation for spacecraft A. Oops, sorry about that. And I believe that is t squared minus 5t plus 20. T squared minus 5t plus 20. And that's going to be our velocity for spacecraft A as a function of time. So what can we do here? Well, if we plot this, we'll notice that the velocity at time t equals 0, it's going to start out at a value of 20. And essentially what we're looking at is a parabola here. And so earlier we talked about how this represents the rate of change of acceleration with respect to time. That's what this bad boy here represents, because we have a velocity graph. The linear term is the acceleration or the rate of change of velocity. This right here is the initial velocity. So if we plot this, initial velocity is 20. After some time, the velocity is going to stop increasing. As a matter of fact, I think it's near immediately. I don't think I plotted this properly. Because right away, the velocity is going to start to decrease, I think. Well, give me 1 second, and I'll bring up Wolfram Alpha, and we'll actually plot it out. On the AP exam, you are allowed a calculator, right? So it's in your best interest to actually take a look at. But I was going to say there's another way here where that allows us to answer this question. But I did want to talk about it like at the most basic level. How do you do it with a basic quadratic? Why didn't it open? There we go. Give me 1 second. It was t squared minus 5t plus 20. And I'm going to go ahead and start doing a screen share here of Wolfram Alpha so we can go ahead and see here. Oh, yeah, I fumbled. Even though the acceleration is negative, I drew a negative quadratic. Whoops. But look here, the quadratic term is actually positive. So see, aren't we glad we actually took a look at it? So give me 1 second. Okay, alrighty, I think I would agree. Let's go ahead and take a look here. So here is Wolfram Alpha. Hopefully you guys are able to see it here. And so we've gone ahead and we plotted the function. And if we look at this, the velocity is decreasing right about at 2.5. Now, in this case, what we're looking for is essentially when does the velocity equal a minimum? Because the moment that it reaches the minimum, it has stopped slowing down, because at some point, the t squared term, which is positive, is going to begin to dominate. And it's going to, and so this entire time we have decreasing acceleration. The acceleration is in the negative direction. That's the slope of this bad boy. But if we notice the slope is decreasing, the acceleration is decreasing in magnitude. And if at some point the acceleration is going to be zero, that's another way to think about it. We said that at a minimum, this should be zero, and or at the minimum, the slope of this should be zero, aka the acceleration or the derivative should be equal to zero. And so we can go ahead and work that out here on our scratch paper, just so that we can actually answer the question analytically instead of just looking at the graph. So I believe we are back on the OneNote, but let me go ahead and make sure it's OneNote. Here we go. All right, I think we're okay. So we were saying that the slope should essentially be zero, aka the derivative or the acceleration. So we take the derivative of this, and we did it earlier. That was 2t minus 5. And we want to solve the expression for when that's equal to 0. So what do we get out of this? You bring the 5 over. I mean, if we want to do a little bit of algebra just to make sure we're doing that correctly, because we can't even graph properly all of a sudden, this becomes 5 equals 2t. 2 of something gives me 5. So we can divide both sides by 2, cancel that out. What do we get? That's 2.5 seconds. Excellent. Very good. So here, if the question is asking during one interval, then it's going to be from 0 to 2.5 seconds. And so here, just to be a little bit more precise in the way they're thinking about it, we'll give it to them in an interval. Now, the action verb here was calculate. So my understanding is that we should have some work leading to this. Now, I apologize, I did not give us enough time here, space here to generate our response, but on the AP exam, you will definitely have that space. Okay, here's the second question, or sorry, part C. Calculate the value of t at which the two spacecrafts are traveling the same speed. So, well, let's see here. If they have the same speed, these two equations gotta have the same value. So let's set them equal to each other. So off to the side here, again, I don't think I gave us enough space. And so we have the equation for spacecraft A, which is t squared minus 5t plus 20. And that has to equal the velocity of A at some time. It's going to have to equal the velocity of B at some time. And let's go ahead and take a look here. Oh no, we're going to have to solve a quadratic, but let's go ahead and take a look here. Oh, well, would you look at that? T squared plus 3t plus 10. Let's see what happens. So we need to isolate our variables. We might be thinking, man, we're going to need to solve this with a quadratic formula, put it in our calculators with a solver feature, but let's go ahead and just crank it out quickly. Looking at this, I'm going to try to move the t squared over on one side, but it doesn't matter which side I choose because minus t squared, wowzers, these terms cancel. So I'm going to go ahead and move this over to the other side like so that I end up with a positive t term right away. And so I'm going to subtract the 10 over, and this is my shorthand way of just showing what I'm doing with the steps. And I'm going to add this over to the other side, and we get 20 minus 10. So that gives me 10. I probably should do all the steps probably, but whatever. I'm afraid we're going to make mistakes. We subtract that over, the 20 minus 10 is 10. And then we're going to add 5t to both sides, and that becomes 8t. At the end of the day, it looks to me like 10 over 8 is the time at which they have the same speed. We can reduce this to 5 over 4, or approximately 1.2 seconds. And so we can go ahead and look at the scoring guide, and let's see if our work is correct. And so scroll down, here's B part 2. And so they take the derivative, that was for B part 2, was take the derivative, set it equal to 0, 2.5 seconds. And they just say t less than 2.5 seconds. So we didn't even have to say 0 less than or equal to, or less than t less than 2.5. So the next part. So again, 1 point is earned for setting the velocity of the two spacecraft equal to each other, and then 1 point is earned for the correct answer. So a nice quick 2-pointer. And so they did the same work we did, and that's 1.25. Sorry, I made a mistake. That's 5/4, 25. I was thinking, yeah, maybe if I hadn't said it, I could BS y'all and be like, oh yeah, 1.25. But no, that's units. So let's actually be correct here. Sorry, I got that a little off, right? I was thinking I was dividing by 5 somewhere there, and so I was thinking 0.2 to think I'm a number sense coach. All right, let's go to the next part. Is the space, and so if you notice there, I would have gotten 1 out of 2 points for that because I did not do the correct calculation. So most unfortunate. This is where you can throw it into your solver, and again, if you have time, confirm that you are on the right track. So we did part C, so that was t equals 1.25 seconds. Is the acceleration of spacecraft A increasing, decreasing, or constant? So here, it pays to have the acceleration as a function of time, which I believe we found to be 2t minus 5. So what's going on here as a function of time? Well, the acceleration is going to be decreasing initially. If we plot this, we start out at a -5. And at some point, the acceleration is going to be 0. We found that out to be t equals 2.5 seconds. And then afterwards, if the spacecraft continues for time greater than that, it's going to be experiencing an increasing positive acceleration. So here I would be careful. Let's go ahead and reference the time in the question. See, okay, so if we look here, the entire interval of the velocity is given through 6 seconds. So it looks to me like this question here, I think, could have been worded a little bit better. But I'm going to go ahead and say check both, and then I would justify my answer. The acceleration of spacecraft A is initially accelerating because the acceleration is in the negative direction and the jerk, or the rate of change of acceleration, is in the positive direction. Or they have opposite signs. Again, the two quantities affect each other in diminishing returns or in diminishing values. And then afterwards, now we're going to have 0 acceleration, but it's still a positive jerk. So our acceleration is going to change in the positive direction. And from then onward, those changes are in the same direction as the acceleration. So it should be increasing afterwards. And so to minimize the clutter, I'm just going to write it in briefly. Initially, decreases after t equals 2.5 seconds, increases. And what is our justification? Initially, A is negative in its sign or direction, and the rate of change of acceleration is positive. Okay, let's go ahead and see here what they were looking for in the scoring guide for part D. And let me know if we have any questions so far. I don't mean to be blazing through this, but I understand that time could be of the essence if you're watching this. So 1 second. Okay. So let's go ahead and see here in the scoring guide. And so for part D, is this the same question? Yeah. D. So 1 point is earned for selecting increasing and then for a correct justification. Okay, so let's see here. Justification at t equals 6 seconds, using the equation, the acceleration is becoming more positive. Interesting. Okay, maybe I must have misread the question. Let's go back. What? I don't know. I mean, I see that after 6 seconds, definitely. I think we agree after 2.5 seconds, it is increasing. But yeah, I just don't think they gave us enough information here in the question to base our answer for which time interval. Now, it could be that when I was copying the question over, I missed part of that for part D. And if so, after enough time has passed, then yeah, definitely it's going to be increasing, especially after 2.5. Okay, so sorry about that. Let's go ahead and look at part E. The following data are collected on the position of spacecraft A and spacecraft B. Both spacecrafts are at position x equals 0 at t equals 0. Some nice data. Plot the data points for the positions of the two spacecrafts on the graph below. Clearly scale and label all axes, including units, if appropriate. Then we're going to draw. So here's one of the things that I feel that many students tend to forget or miss. Oops, that was a rather wild highlight mark. Let's go ahead and try to keep it a little straighter. Draw a solid line that best represents the trend of the data for spacecraft A. And then we're going to draw a dashed line that best represents the trend for spacecraft B. So oftentimes we just plot one thing, but we need to make sure that we have a line that best represents and does not connect the dots. Alrighty, so let's go ahead and take a look here. So plotting these can always feel a little bit intimidating or tedious because the numbers don't look nice and easy, clean to plot as we may be used to in other classes. But what I like to do is I like to look at the biggest values we're going to plot and then look to see if I can get a nice even breaking here. So let's see here. So for time, I think the easiest thing is to put time on the horizontal axis and position on the vertical axis. So for time, we're going to have 5 seconds. Let's see here how many vertical lines we have or demarcations of our graph. I might 1, 2, 3, 4, 5. So they made it nice and easy for us. Here we can go ahead and use each of the major grid lines as our time. Some people may not want to set the last time to be exactly at the edge or the boundary of the graph, but I think for this, it's okay. Now let's go ahead and try to do, and so we should label our axes. And so over here, we're going to be plotting time, and the units for this are going to be seconds. And I don't remember if they told us to do this, but it is important that we do this whether we're asked to or not. Yeah, you see here, so clearly label all axes, including units, if appropriate. So if we were plotting some kind of ratio of like force to force, that wouldn't have units. But in this case, we definitely do because this is going to be position and the units of this are going to be in meters. Now, originally I put the units for seconds in parentheses, but just to kind of keep it consistent with my general notation for class, I like to put units in boxes just so that we understand this is not a variable. This is a unit. This is a little different. Okay. And I don't think I needed to put the axis here. It's in, that extends beyond, but just so that we could see this represents our vertical axis and horizontal axis. Okay, so let's go ahead and look at this. So we're gonna have to plot. Now we have to be careful here. What is the largest value we're gonna plot? Well, we might be thinking for spacecraft A, it's 79, and you would be correct. But overall, we're gonna have to find a way to fit a value of up to 129 on here. So let's see here. 1, 2, 3, 4, 5. 5. I'm going to actually make a little bit more space over here. X, and that's going to be measured in meters. So one way we could do this is round it up. Let's say 130. We go ahead and divide that by 5. That's 2. That's 10. Remainder 3. 30. And then that's 26. So if we plot each major grid line at a value of 26, it may seem ridiculous, but it's going to round up to a nice value, and we will be able to fit all of our data within that boundary. So we'll do 26, 52. We had another 26 to that. That's going to be an 8 and a 7, I believe. We know this has to be 130. And so what's going to be the other value in case you have difficulty adding 26 to that? Take away 26 from that. That's 104. Okay. So these numbers don't look like the numbers you would normally plot on a major grid line. But one of the main concepts for graphing on the AP exam for physics is go ahead and have your graph take up at as much of the region as possible. They say about approximately something like 80%, 70%. And I think this will work. All right, let's go ahead and start plotting these sponsors. At 1, we're going to be at a value of 18. So let's see here, 26. This is where it gets a little tedious. 1, 2, 3, 4, 5. 5 out of 26. Each one of these is 5-ish. So 18, that's going to be about 3 tick marks and above. So about here. The next one, 33. So 26, 30, 33. And oops, I'm already making a mistake. This was at 1 second. At 2 seconds, we're going to be at 33. So that's going to be about right here or so. For number 3, we're at 47. So take away 5 from 52. Would you look at that? This bad boy is right on the line. Of course, 26 divided by 5 is like not exactly 5. It's like 5 and 1/6, right? Or 1/5, but good enough. Let's see here. At 4 seconds, it's going to be at a position of 61. So this is 52. So then add about 10, that's 62. And we're going, yeah, so we'll go ahead and we'll put it right around here. Maybe a little bit lower, but I think we're okay. Right around here, give or take some fudge factor. And then for 5, the last one is 79, which thankfully is right about here. So about a fifth of the way up. Good enough. And then now we have to draw a solid line. So I am not being given the other features that I have on my normal OneNote, but there is a ruler feature here that allows us to draw a straight line. And so this is going to be a little difficult, but we're going to try our best. Sorry, and I apologize for the tablet. Yeah, this is already going haywire. You know what? Nah, we can solve it. Well, I think we get the gist, but yeah, it's not going to work very well on this. Not quite, not my best work. And now it doesn't even want to erase. Let me try bringing up the eraser and see if that'll do it. Oh man, wow, I think OneNote is having some difficulties. I'm gonna go ahead and pause recording here and restart the app. Okay, all right. Okay, so here we go. So we were having a couple of difficulties trying this out. Maybe it's because I was disparaging it for not giving me the ruler feature. But if you can imagine a straight line shifted down in its slope a little bit better, God, this is just terrible. Oh no, I deleted that value, but I think we get the gist of it. This was 79, so about right there. Okay. It's about as good as we're going to get. We'll take it. The next one is going to be 12, 29, and 53. So at 12, that's going to put us, well, shoot, right a little bit under this point, right about the midpoint here. So yeah, about, and you know what? I'm going to do this in blue. So something like that. At 2 seconds, we said it's at 29, so 26, maybe a little bit lower, maybe about there. And then 53, 53 is going to put us right about a fifth of the way up on that mark. And then 85, so that's 78, 83, about here-ish. And then 129, so something like this. Okay. And so we're going to have to draw a dashed line for this. Now, if we look at this, this is almost starting to look a little quadratic. But let's go ahead and we'll worry about that later. So they want us to draw a dashed line, right? So let's go ahead and draw a dashed line. And so it doesn't really look like we're getting a linear fit after about about 3-ish seconds. Something's going on here, but I don't know if they want us to actually draw a parabola to fit that because they do say line instead of curve. So I'd be a little hesitant. Let's go ahead and see what the scoring guide was looking for here. So if we notice, they do draw it as a curve. So, okay, so we were better off going with recognizing that it's a quadratic or a curving function and not just trying to interpolate between the linear portion, which was from like 0 to 3 seconds. Here's another bit of information that I feel, if you notice, they don't extend their lines towards the origin, towards 0, 0. Now, we were told that the position at t equals 0 is 0. So they don't give us this in the table, but they do mention it above. So I think personally, while they did it that way, we do have data going all the way to the origin, which is one of the reasons why I extended it all the way. I didn't draw that point initially, and I'm not trying to like cop out and make a recovery here, but it is one of those that, I mean, I think that shouldn't deny us a point either way. Okay, so let's go ahead and look at the next question. At the point where the two graphs cross, is the speed of spacecraft A greater than, less than, or equal to the speed of spacecraft B? So we indicated that this was going to be occurring during which part? Are they traveling at the same speed? Right here. Here is that portion. We said 1.25 seconds. So let's go ahead and analyze the graph at 1.25 seconds. That's going to put us right about, oops, go back to pen, 1.25. So that's about here, maybe. Because this is 1.2, 1.4, 1.6, 1.82. So yeah, about a little after that right tick mark. So let's see here. At the point where the two graphs cross is the speed, oh, sorry, where the, yeah. They're gonna actually cross over here. I'm not answering the correct question. At the point where the two graphs cross is the speed of spacecraft A greater than, less than, or equal to the speed of craft B. Well, let's see here. Up until all those times prior to their intersection, the velocity of B, the blue graph, was less than that of A, the green graph. Just making sure, yeah. Now, to pass it and have more positions afterwards, when they have the same position, one needs to be going faster. So it looks to me like B is going to be going faster. And so we can approximate that slope here and recognize that the steepness of A, as we interpolate it across those data points, like here, oops, let me not do it in green, but here it was slower than A, which was right here. And then afterwards, it was faster. And so, you know, if I start out behind you and then I'm ahead of you, at some point when our positions are right next to each other, I'm going to be going faster. So the speed of spacecraft B is less than that of A. And so by that justification, let's go ahead and see here how the scoring guide said. And again, the justification being that the slope at the point of intersection is greater for B than A. Or we could say that prior to their intersection, B was behind A, and then it finished after, I'm sorry, it finished ahead of spacecraft A. So it should be faster. Let's go ahead and see here. Speed is the slope of the graph of position as a function of time at the point where the two lines cross. The line of spacecraft C has a lesser slope and thus a slower speed. At this point, I think they're talking about in part C, because that does look like a typo, right? We're comparing spacecraft A and B, and then all of a sudden they're introducing spacecraft C. So I'm going to assume that's an error in the free response scoring guide. Yeah, nowhere in here did they introduce spacecraft C. Okay. All right, so we all make mistakes, yours truly, most notably. So it's okay. I think we get what they're saying. So here's the second question in our PDF. And so we have a bucket and it's going to be connected to a counterweight. And so we're looking at an Atwood machine essentially, except this bucket is going to lose water due to a hole. So it reads, or I'll let you guys read. I don't want to insult your intelligence, but we'll take some time to read it here. And as we're reading through here, my understanding is we are not allowed highlighters on the AP exam, but noticing we have a light string, so we don't have to worry about its mass, whose pulley, a pulley whose mass and friction are negligible, so that makes part of the analysis a lot faster and easier. A counterweight of constant mass is connected to the right end of the string, and a bucket of water is connected to the left end. The counterweight has a mass less than that. Okay, so that's important. And that of the full bucket. but greater than that of the empty bucket. At time t equals 0, the system is released from rest with the bucket full. At the same time, water begins to flow out of the bucket through the hole on the side near the bottom. Okay, so the mass is going to be changing here. Let's go ahead and take a look. The graph above shows the height of the counterweight above its initial position as a function of time between time t equals 0 seconds and the instant the counterweight returns to its initial position. The bucket and counterweight move along after this time. Continue moving along after this time. So let's see here. The instant the counterweight turns to its. So that's my concern here is they say this part, the bucket and the counterweight continue moving long after this time. So if we look at this, I am going to assume the counterweight did not start on the floor. Because if it did reach its starting position and it started on the floor, right? Because we are told that it returns to its initial position. This is the height of the counterweight above its initial position. So this is essentially displacement, not the true height or the final position graph, okay? So this is the relative height above where it started. So we could have very well had the floor here. We could have had the counterweight here. We have our bucket and our pulley. And so initially, this thing is going to accelerate upwards, but then at 3 seconds, it returns. And the reason why I bring this up is because we are told that the bucket and the counterweight both continue to move long after this time, which means that after 3 seconds, after the bucket reaches this point, it's going to continue descending because the counterweight. Because the bucket is losing mass. And so at some point, this will be heavier. And so enough acceleration will be in this direction that it not only does it stop, but it gains velocity and for the counterweight downward and eventually settles on the floor. Anyways, I think that's enough analysis. I think we get the gist of it. Let's look at the question. At time t1, the mass of the bucket in the water is equal to the mass of the counterweight. Which time interval identified below contains the time t1? So we need to find out which of these time intervals represents the time when the mass of the bucket and water, that's one object, is equal to the mass of the counterweight. So we'll go ahead and pause here for a second. Here are our 4 answer choices. So one of them is from 0 to 0.5. I'm not going to mark it that way. I'll just go ahead and say from here to here is one. The other one is from 0.5 seconds to 1.5 seconds. So that's another time interval. The next one is 1.5 to 2.5 seconds. So that's another time interval. And then the last one is from 2.5 to 3. So let's see here. Well, let's go ahead and look at the simplified Atwood machine. If the pulley has no mass, we don't need to worry about its rotational inertia. And if we do enough of this equation, we get, we'll go ahead and say that the initial acceleration this way is going to be in the positive direction. And this guy's going to have its initial acceleration positive in this direction. So if we look at this, initially it's going to be the weight of the bucket. I'm going to go ahead and just write it in a simplified form. The weight of the bucket and water. That could be a little confusing. So W for weight, and then B for the bucket, and W for the water. Minus, and then so if we look at the forces here, yes, we have the weight of this bucket acting down with water. But we also have the weight of the counterweight. So we're going to do minus the weight of the counterweight, and that's going to be equal to m times a. We have a nasty differential equation that can pop out of this. But we don't need to know about any of that right now because they tell us that at some point these two are equal, which tells us that all this cancels out. So that tells us that the acceleration is zero. How the heck are we going to get the acceleration is zero here? Well, if we remember, second derivative of position with respect to time is the acceleration. This is represented by the concavity or the curvature. So let's go ahead and see here. Well, what kind of curvature do we have? Oh, well, we have positive curvature, so positive acceleration. So that's the way we defined it. And then over here, we have negative acceleration. Yeah, exactly. So in calculus, I think you learned the second derivative test, where if the second derivative is equal to zero, you have an inflection point. And if we look here, we have part of a positive parabola converted into a negative parabola, and it happens right around 1 second, approximately 1 second. There's another way to think about it. If the acceleration is zero, we're looking for a constant slope on a position graph, position time graph, sorry. Constant slope, because if the acceleration is zero, the velocity is constant. And this is the same thing as saying the slope of a position graph. Okay. So looking at this, looks to me like interval number 2 is our best bet. And so there we go. Let's go ahead and take a look at the scoring guide, see what they were looking for. So for this portion here, 3 points for this one. 1 point for an answer of interval 2. Let me zoom in a little bit more so that we know what I'm referring to here. Okay. And then 1 point is earned for an indication that this time interval includes zero acceleration or some equivalent kinematic idea, such as the bucket stops speeding up and begins to slow down, or for an indication that the graph is concave up before this time interval and then concave down after this time interval. So in this time interval, there's a point of inflection where the acceleration switches signs. This means the acceleration must pass through zero. And then a third point is earned for an explanation indicating that the acceleration is zero when the force is balanced, so that so this is when the masses are equal. And that's what we did by writing Newton's second law there. So very nice. Let's go ahead and look at part B. At what time is the potential energy of the counterweight Earth system a maximum? Justify your answer. We're going to talk about this one because I think there's a couple ways to think about it, but I'll let you think about it here for a second, see what comes to mind. Okay, so let's go ahead and take a look here. There's a couple of ways, especially with knee-jerk reactions, that we may be thinking about this because, well, let's go ahead and see here. Height. We're talking about potential energy. Now, we don't have any springs. So essentially, the height here represents a position of gravitational potential energy change from its reference point. So here, this is really, if we multiply this by mg, well, mg times the change in height, and so this is the height change from its initial position, zero. Well, this is really going to be a graph of the gravitational potential energy. So upon first instance, we look at this and we say, okay, well, the more height I have, the more gravitational potential energy. And so it looks to me like at 2 seconds, we're going to have the most gravitational potential energy. There's another way to think about it. The potential energy is going to be greatest when the velocity is zero. So when is the velocity zero? Well, velocity information is represented by the derivative or the slope as a function of time. So maybe initially we have zero slope. We'll talk about that here in a second. And maybe we're thinking over here. the velocity, aka the slope, is 0. And so that's another way to justify why you think 2 seconds would be when the slope or when the gravitational potential energy or the potential energy, as the question asks it, is at a maximum. And let me just make sure here I resumed recording because, okay, just making sure for the. So I think that's good enough for I guess what the College Board is looking at. Here's what I want us to say though. One, energy is going to be conserved if we wanted to use the kinetic energy B minimum yields maximum potential energy argument in a closed isolated system or in a closed system. My concern is that the bucket is losing mass and therefore the system is losing mass and therefore going to lose potential energy as the bucket drains. So I actually think this question is a little bit more complicated than it lets on, because by the time the counterweight reaches its maximum height, I do agree that it itself has the most potential energy. But what did it start out with? Well, we started out with the bucket at the top. And when the bucket is at the top, it's heavier and has more mass than the counterweight. So the system starts out with more potential energy with the bucket being at the top with water than the counterweight being at the top, even reached the same height, which I don't think is going to happen. So it looks to me like overall, because the system loses mass, it may be losing gravitational or potential energy from the moment the bucket starts to lose water. So it's a little bit more complicated than that. Here's another thing I would say. Let's say energy, all of this is happening in a gravitational field, which is a conservative field. We've learned that the force is represented, whoops, that F came out a little funky. And I think that we can make counter arguments to what I'm about to say, but let's go ahead and take a look at this. We've learned that the force from a conservative field is going to be the derivative of that potential with respect to position. Now, this potential is really going to be like mg times h as we change heights. But this is not constant. But ultimately, the way I see it is if we're plotting potential, we have a maximum or a minimum of potential energy when its slope is 0. So when this is equal to 0, we are at a maximum or minimum by the definition of like minimums and maximums in physics and calculus, right? So another way we can think about it is if the derivative of position with respect to the height here is 0, then we have 0 force. So I think this is a little complicated because if we multiply this by mg, this function here is going to yield the force. The problem is if we just take the derivative of a height function, that's going to give us the velocity. So we kind of have a misconception here. We would ultimately need to write this function also, or the potential energy function with the mass as a function of height and or time to really get a good analysis. Because when is the force equal to be 0, or when is it going to be equal to 0? The force is going to be 0 here where the acceleration was 0. And if the acceleration is 0 at this point, then the net force on the system is going to be 0. And so the force is 0. And if the force is 0, we have reached a maximum or minimum of our potential energy function. So this is where I'm a little cautious with calling this height graph here a potential energy graph height function, or sorry, potential energy graph, because it's not quite, because the mass is also changing as time goes on. So if we had a constant mass, then I would agree that this height graph is really a potential energy graph, but it's not. But ultimately, looking at this, if the acceleration is 0, the force is 0, so we might be thinking, okay, maybe at 1 second, maybe at 2 seconds. Let's go ahead and see here what the College Board is thinking. And hopefully those ramblings kind of made sense. Because at the end of the day, I think this question is a lot more complicated than the immediate answer we might be thinking. So They say 1 point is earned for t equals 2 seconds with an attempt at a justification. Oops, I did not mean to write. 1 point is earned for indicating this time is when the counterweight is at a maximum height, and then, or zero velocity. And then 1 point is earned for stating that the potential energy of the counterweight system is proportional to height, or stating that U is maximized when K equals 0. Now here's something that they do say. Note that if the student explains the potential energy of the entire system decreases beginning at time equals 0 because the water leaks from the bucket and makes no incorrect statement, they earn 1 out of 3 points. So they're recognizing that on some level, this is a correct analysis, but it's not the complete or best analysis they're looking for, because to get full credit, we got to be saying what they're saying over here. At the end of the day, I kind of don't agree with that, but they're the College Board, right? They definitely know more than I do here when it comes to this scenario. So be careful, but at least these are some of the thoughts I had. So let's go to the next question. And if anyone has questions, feel free to ask. Alrighty. So let's see here. Excuse me 1 second. I'm gonna drink some water. I'm a little thirsty. The students approximate the acceleration of the counterweight using the function a of t is given by 1.8 minus 1.8 t for an interval of t greater than 0 less than 3 seconds. Note that positive acceleration represents upward acceleration for the counterpoint. So does this acceleration function match, or sorry, describe? So we have to use words here using the action verbs of the College Board. Describe. Describe how this acceleration function matches the given position versus time graph above for the counterweight of the counterweight during this time interval. So nowhere here do we have to talk about how it disagrees or any of that. Let's just see here, what do they say in common? Well, if we'll notice this, automatically the acceleration of 1 second is going to be 0. So let's see here if we agree with that. Also, it says that the acceleration of 0 seconds is going to be positive, and the acceleration for t greater than 1 second, it's going to be negative. And it's just going to keep on increasing indefinitely. So at 1 second, what did we say? Oh yeah, the acceleration is 0. So we're in agreement. Do we know the initial acceleration? We cannot get that from this information. So we're kind of there. But if we notice, what kind of concavity do we have? We have positive acceleration. We have a smiley face. So it also agrees in that aspect, in that the initial acceleration is positive and upward. So concave up, or positive parabola. And if we notice, the curvature itself is decreasing, right? We have this inflection point at 1 second. So the acceleration is decreasing all the way up to about, well, let's see here. The acceleration is 0, yeah, at 1 second. The part where I think it begins to change is after 1 second, we do get an increasing negative acceleration. And that's what, I'm sorry, let me make sure I'm saying that. Yeah, because we're going to go from 0 acceleration, 0 curvature, to maximum curvature downward by the time we get to this other portion. So, but I don't think the acceleration here is going to grow indefinitely, because at the end of the day, unless we cut this cord, the acceleration of this counterweight will be less than 9.8 downward. Okay, so unless the cord is cut, because we have an Atwood machine, right? The inertia of this bucket, even when it's empty, it still affects the acceleration of the system, because at the end of the day, it's the difference in their weights, that's the net force. And then we divide that by the net mass of the system, and that would give us the acceleration of the system. So it should be less than 9.8 at the end. It shouldn't just grow infinitely downward. So how does it match? It matches in that a of 1 second equals 0 meters per second. The initial acceleration is positive, but decreases in value. until t equals 1 second. Oops. And I'm forgetting units. There we go. Afterwards, the acceleration increases in the negative direction. All right, so that's this question. And then the follow-up, explain why this function does not correctly model the acceleration for a long period of time, assuming the system is able to move for a long time. Well, ultimately, a of t would grow indefinitely, but the system will reach and I put and because I was going to say an acceleration, but more specifically, a downward acceleration less than free fall because it's not falling freely. Okay, so there we go. Okay, and even so, here's a statement. And sorry, let me pause the recording. Alrighty, so let's go ahead and see here. The students are told that the mass of the counterweight is 10 kilograms and the mass of the bucket, and it's approximate in it, and of the mass of the bucket with water in it is approximately given by the equation 14.4 e to the negative 369t kilograms for t less than 8 seconds. Assume any action-reaction forces between the bucket and the water draining are negligible. Explain how the students could use this information along with the acceleration to calculate the total linear momentum of the system consisting of the bucket, the water in the bucket, the pulley, and the counterweight at time t equal 3 seconds. So this question here is going beyond kinematics, but I think we should take a look at it because, I mean, at the end of the day, the AP exam is going to throw you free response questions that tie in multiple topics at once. And so right now we're reviewing for kinematics, and the kinematics portion of this question is over. Now let's go ahead and take a look. So we want to find the total linear momentum. So it started from rest. So we know that the initial momentum is going to be 0. So essentially, the total linear momentum at the end of the entire system, including buckets, pulleys, waters, the earth, and all that jazz, that's going to be the same as the change in momentum. So we may be thinking, well, how do we find this change in momentum? Well, in physics 1, we have impulse, where the force times some change in time is going to be equal to the change in momentum. And this is very nice and easy for constant forces. Or if the force is not constant in physics 1, we were usually given a graph of sorts that we could get the area under. And that's the main motivation, because at the end of the day, delta P, the change in momentum, is going to be the integral of the force as a function of time with respect to time. And that's really what we're doing here. We're going to add up a bunch of tiny little delta T's. The tricky part here is the force is not constant. So how are we going to get this force? This is the net force on the system. Well, how do we get the net force? Well, the net force from Newton's second law, which is also a rewriting of this form here. But we're going to do the left-hand side. It's the sum of the, it's m times a. Now here we have to recognize that the mass and the acceleration are not constant. The acceleration here was given to us in a previous question, and the mass was given to us here as an equation, e to the negative 3.369 t. The acceleration is going to be 1.8 minus 1.8 t. Now let's go ahead and see here, because ultimately what I am doing here is I am deriving, and this action verb is explain. So all we really have to do is just explain. We don't actually have to do this calculation or carry it out. But the idea is we can integrate m of t times a of t from 0 seconds to 3 seconds to find the impulse. That's what we're doing here. The impulse on the system is the change in momentum. So here we could say which is the change in momentum of the system. Okay. And so just in case, impulse is the change in moment. Oh, we already said that. Sorry. What I'm trying to say here now is, and this change represents, since the system started at rest, had no momentum initially, linear, we have to be specific here, but I'm just going to go ahead and not write it, but we're talking about specifically linear momentum. And so linear momentum is going to be force along time, linear, not torques, right? Had no momentum. So the total is the change. And I don't even think we have to write this much, just to be, specific enough for the audience. So the total value, whoops, not values, is the final quantity. All right, so that's this question. Let's go ahead and take a look here at the scoring guide, see what they were looking for. So, and here they are going about their explanations for when is the acceleration, or when is the acceleration equation equivalent and not. But let's go ahead and see here. So for part E, because the prompt says explain, a student cannot earn all 5 points without writing any prose. So we have to be careful. I'm glad we mentioned this part, because we have to be careful with the action verbs. And I did post those in the Google Classroom so that we know what is expected of us when they say these specific terms in the questions. If equations are written that satisfy all 5 points, but no prose is provided, a maximum of 4 points is earned. So 1 point is earned for indicating how the bucket's mass function could be used to calculate its mass at a given time. An explicit statement that the bucket and water mass will be 4.76 at 3 seconds would also give us this point. Note, m of 3 earns this point. Okay. 1 point is earned for a description of taking the integral of the acceleration function to get the velocity, or integrating MA. 1 point is earned for explicitly stating the limits. Oof, we did not get this point. I apologize. From 0 to 3 seconds, we are being we have to be very specific here, because they did ask specifically about at 3 seconds. So we should have our bounds here. So integrate, oh wait, no, we did say from 0 to 3 seconds. Okay, never mind, sorry. I just didn't write it over here. 0 to 3 seconds, okay, good enough. Well, this is where it pays to explain it instead of just writing the equations, right? Okay. My equation was a little off, right? I was thinking that was the mass of the system, but we need to take away the mass of the counterweight from it. If a student discusses taking the integral and receiving the previous point, and then says that the speed of the system is 2.7 seconds, then this point is earned. And then 1 point is earned for an explicit remark that the velocity of the counterweight and the bucket will have the same magnitude but different sign. Okay. And then we could have also earned that point by explicitly stating the accelerations of the bucket and counterweight are in opposite directions, such as here. Okay. Wow, they did a lot more work than what we wrote for this question. So I'll give you guys some time to read that. Okay, so I did want to harken back to a mistake here that we caught as we were explaining that last part. I wrote this as the net force, but we have to be very careful here because this here represents the mass of the bucket and water. This is not taken into account the counterweight. The counterweight itself is creating a force in the opposite direction and therefore trying to cancel out the change in momentum of the bucket and water. So at the end of the day, we're going to have the bucket and water with a velocity downward initially. Well, actually, it's going to be after enough time passes. I think here, did we determine when it reverses direction? The height is reached at 2 seconds. So, and we're talking about at 3 seconds. At 3 seconds, we do expect that the counterweight is going to be dropping. So the counterweight is going to have velocity down, so its momentum is going to be downward, which is a vector quantity, and the bucket with water is going to have velocity and momentum in the upward direction. So we have to add these two vector quantities, but what do we do when these two vector quantities point in opposite directions? We subtract it. So one way the more correct way to have written the integral for this, as we saw there in the scoring guide, was that from 0 to 3, it's not just the force on the bucket, but also the counterweight. So there's a couple ways we can write that. Negative 3.369 t. The important thing here to recognize is that they both have the same magnitude of acceleration. It's just that the bucket is acting in the opposite direction as the momentum of the counterweight. So here I'm just going to go ahead and subtract the mass of the counterweight. And then we can go ahead and multiply that by their acceleration. There we go. And I think that is a more precise way of actually calculating this. Now, they do use the word explain. So I don't think we explain how the students could use this information to determine the total linear momentum. So here, I don't think we actually have to carry out the calculation. And so I think this is sufficient. But if we look at the scoring guide, they did go into a little bit more detail in the numerical analysis, as we can see here. Now, I am in the belief that generally what we did is sufficient to explain, but if you do find yourself having enough time, go ahead and crank all this out. Okay. So let's go ahead and see here. It's 8 o'clock. I think we'll pick this up and we'll do these next questions. Let's aim for tomorrow. I'm thinking we're going to do Monday, Tuesday, Thursdays review sessions. And so I think we have like 2 more questions here remaining. And so three actually. We do have 3 more questions remaining. So we'll go ahead and crank those out next time. If you guys wanted to go ahead and take a look at the PDFs and attempt the questions on your own ahead of time, you're strongly encouraged. Thank you for tuning in. We'll catch you guys next time. Have a good one. I'm going to go ahead and stop recording here.